In this video series, we will introduce parallel algorithms and its core concepts. First, we will discuss the basic idea of how parallel algorithms work in a real-world scenario. Then we will go in depth in parallel algorithms. We will discuss the architecture of parallelism, which can vary from control mechanism, address space organization, and interconnection network. The next several videos will go on with the PRAM model, a theoretical model which is a mere extension of the computational serial model, and then we'll provide you example codes to show you parallel algorithms in action. Given a scenario where you want to build a fence in your backyard, and it's necessary to dig 10 deep holes, one for each fence post, until you realize that it would be completely laborious task to do for an individual to dig the 10 holes in sequence. So you search for an alternative. So you try to promote to your health-conscious neighbors about a competition for hole digging in your backyard, and whoever is the fastest wins the contest. During the competition, 10 strong neighbors simultaneously dig 10 holes. This is called digging the holes in parallel. Instead of doing the digging by yourself, you have saved yourself a lot of work and completed the hole digging much faster than you would have done by digging them in sequence by yourself. Often, a computer can complete a job faster if it has many processors executing instructions in parallel. Just as you can complete the hole digging job faster by having friends work in parallel. Previous algorithms have been designed to be implemented on a traditional sequential computer, where a single computer has one processor executing instructions in sequence, like the example given a while ago in digging the 10 holes in sequence by a single person. These computers are based on the model introduced by John von Neumann. As figure 12.1 illustrates, this model consists of a single processor, called the central processing unit, and memory. The model takes a single sequence of instructions and operates on a single sequence of data. Such a computer is called a single instruction stream, single data stream computer, and is properly known as a serial computer. The previous example provided is relevant to parallel computing. Parallel computing is where each processor can execute instructions simultaneously, in parallel, with all the other processors. It had decreased the cost of processors dramatically over the past 3 decades. There are many applications that can benefit significantly from parallel computations. Let's go more into detail. We'll start with parallel architectures. The construction of parallel computers can vary in each of the following 3 ways: control mechanism, address space organization, interconnection network. First is control mechanism. Each processor in a parallel computer can operate either under the control of a centralized control unit or independently under the control of its own control unit. The first kind of architecture is called single instruction stream, multiple data stream. In a SIMD architecture, the same instruction is executed synchronously by all processing units under the control of the central control unit. In general, SIMD computers are best suited to parallel algorithms that requires synchronization. SIMD computers are suited for programs in which the same set of instructions is executed on different elements of a dataset. Such programs are called data parallel programs. A drawback of SIMD computers is that they cannot execute different instructions in the same cycle. Parallel computers in which each processor has its own control unit is called multiple instruction stream, multiple data stream computers. MIMD computers store both the operating system and the program at each processor. Many MIMD computers have extra hardware that provides synchronization, which means that they can emulate SIMD computers. Next is the address space organization. Processors can communicate with each other either by modifying data in a common address space or through passing messages. The address space is organized differently according to the communication method used. In a shared address space architecture, the hardware provides for read and write access by all processors to a shared address space. Processors can communicate by modifying data in the shared address space. Figure 12.4a depicts a shared address space architecture, in which the time it takes each processor to access any word in memory is the same. Such computer is called a uniform memory access computer. In an UMA computer, each processor may have its own private memory. As shown in Figure 12.4a, this private memory is used only to hold local variables necessary for the processor to carry out its computations. None of the actual input to the algorithm is in the private area. A drawback of UMA computer is that the interconnection network must simultaneously provide access for every processor to the shared memory. Another alternative is to provide each processor with a portion of the shared memory. This is non-uniform memory access computer, and it's illustrated in Figure 12.4b. This memory is not private, as is the local memory in Figure 12.4a. That is, each processor has access to the memory stored at another processor. However, it has the faster access to its own memory than to memory stored at another processor. If most of a processor's accesses are to its own memory, performance should be good. In a message passing architecture, each processor has its own private memory that is accessible only to that processor. Processors communicate by passing messages to other processors rather than modifying data elements. Figure 12.5 shows a message passing architecture. Notice that Figure 12.5 looks much like Figure 12.4b. The difference is in the way in which the interconnection network is wired. In the message passing computer, it is wired to allow each processor to send a message directly to each of the other processors. Finally, we proceed to interconnection networks. There are two general categories of interconnection networks: static and dynamic. Static networks are typically used to construct message passing architectures, whereas dynamic networks are typically used to construct shared address space architectures. A static interconnection network contains direct links between processors and are sometimes called direct networks. It should be clear that the reason why static networks are ordinarily used to implement message passing architectures is that the processors in such networks are directly linked, enabling the flow of messages. The most efficient but also the costliest is a completely connected network, which is illustrated here. In such a network, every processor is directly linked to every other processor. A processor may then send a message directly to another processor over the connection to that processor, since the number of connections is quadratic in terms of processor numbers. This kind of network is very costly. In a star-connected network, one processor acts as the central processor. That is, every other processor has a link only to that processor. The illustration depicts a star-connected network. In a star-connected network, a processor sends a message to another processor by sending the message to that central processor, which in turn routes the message to the receiving processor. In a bounded degree network of degree d, each processor is linked to at most d other processors. The illustration shows a bounded degree network of degree 4. In a bounded degree network of degree 4, a message can be passed by sending it first along one direction and then along the other direction until it reaches its destination. A slightly more complex but popular static network is the hypercube network. A zero-dimensional hypercube consists of a single processor. A one-dimensional hypercube is formed by linking the processors in two zero-dimensional hypercubes. A two-dimensional hypercube is formed by linking each processor in a one-dimensional hypercube to one processor in another one-dimensional hypercube. Recursively, a d+1 dimensional hypercube is formed by linking each processor in a d-dimensional hypercube to one processor in another d-dimensional hypercube. Another interconnection network is a dynamic interconnection network. In a dynamic interconnection network, processors are connected to memory through a set of switching elements. It should be clear why dynamic interconnection networks are ordinarily used to implement shared address space architectures. That is, in such networks, each processor is allowed to access every word in memory but cannot send a direct message to any of other processors. One of the most straightforward ways to do this is to use a crossbar switching network. In such a network, P processors are connected to M memory banks using a grid of switching elements as shown in figure 12.8. If, for example, processor 3 can currently access memory bank 2, the switch at the grid position circled in figure 12.8 is closed. Closing the switch completes the circuit, enabling the flow of electricity. This network is called dynamic because the connection between a processor and a memory bank is made dynamically when a switch is closed. A crossbar switching network is non-blocking. That is, the connection of one processor to a given memory bank does not block the connection of another processor to another memory bank. Ideally, in a crossbar switching network, there should be a bank for every word in memory. However, this is clearly impractical. Ordinarily, the number of banks is at least as large as the numbers of processors so that, at a given time, every processor is capable of accessing at least one memory bank. Other dynamic interconnection networks which will not be discussed here include bus-based networks and multi-stage interconnection networks. Thank you for watching. This is the end of the topic on Introduction to Parallel Algorithms. You can continue learning more about parallel algorithms by clicking on one of the videos in the playlist. The videos would go on with the PRAM model, a theoretical model which is a mere extension of the computational serial model, and also videos about getting deeper on parallel programming by having a hands-on approach.